It's the opposite of what you think.
Yeah.
If the sun is out, then you have more winter. If the sun is not out, you don't have winter. So, I mean, I'm guessing based on today, the sun's out. But what about in Punxsutawney, Philadelphia? He's the official groundhog, I think. Punxsutawney Phil. Does anybody know? Did it see his shadow?
It did.
You did?
Yeah.
Is that a good thing?
No.
It's the same thing. Did you ever see that movie, Groundhog Day?
Yeah.
It's fantastic. Nice hat.
Thank you.
You're rocking the Carhartt.
Yeah.
I almost wore my hat like that. I'm excited to wear this. How's everybody doing today? Good. Hello, Megan. What's the matter?
I was looking for restrooms, and I come from Fuller.
Oh, that's like practically in Centerville. So you went from Holwager's class to a restroom somewhere and then here.
Which I'm actually very proud.
With a one-way hall. And that was a 10-minute. How long do you have between classes? 8. Which restroom did you go to? The one in West?
Yes.
Okay.
Is this West?
Yes.
Yeah.
What year in school are you?
I've never gotten that down.
This is West Unit.
Yeah.
Okay. All right, well, let's do some integration by parts. You excited about that? Did you work on those last night? Did it go better? Annie says no.
I mean, I got like 1 or 2 more, but still struggling.
So there was one yesterday that someone had asked me about in the second period. I mean, in the next period, second class. It was number 23. And when I first looked at it, like it took me a second I didn't recognize like, what it was. Most of these I can look at because I've done a million of these and like say, oh, this is that, this is that. But that one, for some reason, I looked at it and I was like, ooh, I don't know how to do that one right off the top of my head. So it took me a second. So I want to make sure we do that one together. Because what ends up happening in that is something that you need to experience. And that's when you feel like you're going to start going in circles. Did anybody have that? Where you were working these problems and you're like, wait, I'm going in circles here. So we're going to do 23 for sure. We finished that inverse trig function right at the end of class yesterday, right? We didn't finish it. Oh, so what was that one? Do we remember? Let's start with that. Was it inverse tangent or inverse cosine? Was it 5x? 2x. I knew it was something x. So if we start this off, we're going to say that u is inverse cosine of 2x and dv is dx, right? And then du, what's the derivative of inverse cosine? Well, it's -1 over the square root of 1 minus 2x squared times 2. Because that's the chain rule, right? And then v is going to equal x. So when I do the integration by parts formula, I get x inverse cosine 2x minus the integral of v du, that's going to be negative 2x over square root of 1 minus, and I'm going to go ahead and just say 4x squared there, dx. Okay? So now you're there. Now, hopefully you know how to do this one. Because if you get here and you don't know how to do this, then you're kind of in trouble, right? Now, how do you do this one? This is a u sub, right? So what's u equal? This is probably a little bit more of an involved u sub than we're probably comfortable doing in our head. So I'm going to put a little bracket there just to set this off. What's u?
1 minus 4.
Yeah, I think we got this far yesterday, right?
Yeah.
U is 1 minus 4x squared. So then du is negative 8x dx, right? So du over negative 8 equals x dx. So now when I substitute that back in, I get 2 du over negative 8, I'm going to put it like that, over the square root of u, which is the same thing as negative 1/4 u to the negative 1/2 du, which is the same thing as, or when I anti-differentiate this, what happens? What's the antiderivative of that there? What do you get?
Of u to the negative 1/2.
So we got to anti-differentiate u to the negative 1/2. What is that?
2u to the 1/2.
2u to the 1/2. Okay? And 2 times negative 1/4 is going to be negative 1/2 u to the 1/2. Right? So now when it's all said and done, go back and resubstitute. We're going to have negative 1/2 u to the 1/2. What was u? 1 minus 4x squared. So that's all of that in there, right? Now I got to combine that with this guy right here. Yeah.
Oh, you forgot the negative, like the 2 over rather than the u up there. 'Cause it's-
Say where
The
now?
2 should be negative, like that.
These two?
Yeah, that should be negative.
Well, isn't it negative because, or isn't that the?
Oh, would it not make it?
Oh, I see. This two never was, I see, yeah. This 2 right here should still be negative. The du is negative, so this is actually going to make that positive, right? Which is going to make that positive, right? Good catch, thanks. So now this isn't our final answer. What do we do with this? He has to get combined with this guy right here. So our final answer is going to be x inverse cosine of 2x. And we decided that was a plus, so minus 1/2 square root of 1 minus 4x squared. Plus chips. Okay? Yeah. Any others other than 23? I want to work that one out for you, but any others? Yeah.
About 35.
What's that one?
The antiderivative of x times the inverse of x.
So we're kind of at a loss here because we're not at a loss, I guess. We only really have one choice right now for what could be what. I can't let dv equal inverse secant. Why? I don't know the antiderivative of that, right? I don't know the antiderivative of inverse secant. So I guess I'm going to start with let u be that and see what happens. Okay? So let's say u is inverse secant of x, then dv is x dx. Now, this is kind of poopy because I don't know if we know the antiderivative of, or I'm sorry, the derivative of inverse secant. That's not one of the ones I told you should know back in the fall when we learned those derivatives. So maybe we should look that up real quick. What's that? Photomath knew it? Oh, that photomath. Okay, that photomath. Does photomath know how to integrate by parts? Really? Impressive. So what did photomath say the derivative of inverse secant was?
1 over x squared, and then radical 1 minus 1 over x squared.
1 over x squared? Radical what?
1 minus 1 over x squared.
Yeah, I don't like the way that's written. Because I think what that is something that's equivalent, but I don't know if that's going to help us. With
They ended up crossing out a bunch of stuff and simplifying it.
I think it's x times radical x squared minus 1.
I don't think the first x is squared.
A lot of books have a table in them. Your book is lame. So, yeah, the antiderivative of inverse secant that the derivative of inverse secant that I like is this. Now, what did you tell me it was, Megan?
1 over x squared, radical 1 minus 1 divided by x squared.
Are those equivalent?
Yeah,
Are you just saying that?
I got the same answer.
Let's see. All right, so if I let du be that, then what's v? We're still, so x squared over 2, right? So now I've got u times v, x squared over 2 times inverse secant of x minus the integral of v du. I forgot dx here, by the way. But I don't care if you forget it. I'm not going to scream and yell if you forget it there. So v du, ready? X squared over 2, x square root of x squared minus 1 dx.
Why does the 2 go on top of?
Well, I'm going to just take it out and put it as a 1/2 right now. This is equivalent, Becca. And let's go ahead and simplify. X squared over x becomes that. Are you okay there?
Yeah.
Okay, so how do I do the next step? What am I going to do here? This is the u sub, right? So x over 2, or x squared over 2 inverse secant of x minus 1/2. U equals x squared minus 1. Du is 2x dx. Du over 2 equals x dx. So this is u to the negative 1/2 du over 2. And then what's the antiderivative? Oh, I feel like we just did that one. What's the antiderivative of u to the negative 1/2? 2u to the 1/2. And what's going to happen with that 2 and that 1/2 there? Them's going to cancel, right? So we get u to the 1/2. And what was u? X squared minus 1. So final answer here is what? X squared over 2 inverse secant of x minus 1/2 radical x squared minus 1. Is that what photomath gave you?
Yes.
Really?
Uh-huh. They ended up crossing out a bunch of stuff.
Yeah, we crossed out a little bit too. I'm curious as to why photomath decided to write that derivative that way. That's one of the, I mean, photomath could be a very useful thing, but it's one of those things where, you have to be careful, because if it does something, you have to understand the equivalency, right? I mean, that, you're not going to look up in any book the derivative of inverse secant and find it written that way. It'll always be written like this. In fact, it'll actually be written with an absolute value there, but that ends up not mattering. Plus chips. Lost the chips. Lost the chips. Who doesn't love integration? Is it tedious? It is tedious. Sometimes, I don't know if I said this in here yesterday, integration by parts is almost as much of an exercise in bookkeeping and being neat as it is calculus. Because you really have to keep yourself organized on your page. If you're one of these people that just write stuff all over the place and kind of like me, sometimes ADD on paper, integration by parts can be hard because you got to really keep things organized. Okay, other ones? Yeah.
You do 25.
Tell me what it is.
Ln of x squared.
Natural log of x, quantity squared, or natural log of x squared?
Like the whole thing.
Okay. Oh, yeah, this is a good one. Like this. Okay. So you have some options here. Because if you remember, when we did natural log of x the other day, we said natural logs make great u's, right? So one option might be just to let u equal that whole thing. And dv equal dx. Okay? Another option might be to think of it like this. And let u equal 1 and dv equal the other. Okay, we'll try it both ways, see what happens. Which way do you want to do it first? Annie, this is your problem, you tell me. The first way? So we're going to say u is natural log of x squared, dv is dx. So du is 2 natural log of x times 1 over x. How do we get that? Where did this 1 over x come from? Chain rule. Okay, good. I love you guys. What's what's x? Sorry, v. I just told you. X, okay? So it's x natural log of x squared minus the integral of v du. So that's 2 natural log of x times 1. Oh, I forgot dx here again. I always do. 2 natural log times 1 over x times x dx.
Can you cancel that out right away?
Factor that out. What do you mean, kid?
Cancel it out. The 1 over x.
Hell yeah! Absolutely. You mean, but don't even write it down?
Yeah.
Absolutely. I mean, if you were asking me to do this on my own, I would totally have done that. Now you got to be careful because if you get too cancel happy and too simplifying happy in the midstream, like, you know, you can get careless. Just get carried away with canceling. So Becca says I'm going to end up with this. Right? Now, I would say we can do this antiderivative by parts. Okay, we can do it again by parts. But I would say you probably want to stick that in your hip pocket. You want to probably have the antiderivative of a natural log available to you. It's just easier. It takes less time. Okay? If you went back and looked in your notes from yesterday or 2 days ago, you'll see the antiderivative of natural log is x ln x minus x. And then that's going to all get multiplied by 2. And you can just leave it like that. So, plus the chips. Okay, now just for funsies, is it possible we could have done it this way? It's not very often that we get this opportunity where you could do it a couple different ways and it works out. So what's du if we do it that way? Du is 1 over x. I'm not going to forget the dx this time. And what's v? Okay. So u times v minus the integral of v du. Becca, do you want to simplify that right away, or do you want to just?
I wasn't there yet. I don't care.
I can't do that. I'm not doing that in my head. I'm too afraid. I know my limits. So if I distribute this 1 over x, what do I get here? ln of x minus 1. Yeah? So now I have natural log of x natural log of x, minus, okay, so I can do this guy term by term. So the antiderivative of natural log of x is x natural log of x minus x, and the antiderivative of 1 is x. Plus chips. So the question is, I mean, you know, what's my question? You guys know the question I'm going to ask. You should know the question I'm going to ask. Are those equivalent? Right? Are those equivalent? I mean, they better be. They have to be equivalent, or they have to differ by a constant. Are these two equivalent? If I distribute this and then combine like terms and do all that, am I going to get this? I am. If you don't believe me, check it. There's the XL and X squared. There's XL and X, XL and X. That's going to give you minus 2 of them. Okay. That was fun. That was fun. I feel like I've given them that problem on a quiz before, or a test before. I feel like that problem pops up around. It's a pretty popular one. Okay, friends, what else? You ready to do one of the harder ones, like the circular ones? Ross, what were you going to ask about?
I was going to ask about 37. My answer was x sine of h of x plus cosine of h of x. The book said it was x sine of h of x minus cosine of
Okay,
h.
hold on. H.
That's what I got that.
Yeah.
Hold on a second. Sine h of x like that?
Yeah.
Photomath didn't know
Photomath didn't know that one? I'm surprised you know. How did you know what to do with that? Like sine h.
I just ignored the age.
You just ignored that h?
The answer was like super simple.
So interesting. Like I don't remember. I mean, sometimes I purposely give you ones that I know you're not going to know how to do because I want you to experience it. But I don't think that was the case in this one. 45. What number was that?
37.
Yeah, do you guys know what that function is? So, at least after you've had this experience, you're going to remember these functions. But I'm not going to make you do this. Like, these are what's called the hyperbolic trig functions. Hyperbolic sine and hyperbolic cosine. What those functions are, hyperbolic sine is actually equal to this. Oh, shoot. I want to just, I don't want to tell you and be wrong. 1 over e to the x plus b. I think it's this. Don't quote me on that just yet. I'm going to look it up just to verify. I'm like 90% sure that that's what it is. Okay? That function right there, e to the x plus e to the negative x over 2, is given a special name. It's the hyperbolic sine of x. Okay? The reason why they give them this name of hyperbolic sine and hyperbolic cosine. By the way, hyperbolic cosine would be the derivative of this. So it would be this. The reason why they're called the hyperbolic trig functions is because their derivatives behave like the trig derivatives. Okay? They're also called hyperbolic because they sort of look like hyperbolas in their graphs. All right? Now, I will tell you the most significant thing about these functions, the hyperbolic cosine or hyperbolic sine. I would argue probably the most significant things about these functions is that if you take a cable or a string or a rope and you hold it at this end and you hold it at this end and just let it dangle with gravity. Okay? So like a telephone wire. If you see a telephone wire going across the road, it's like dangling, right? That curve is a hyperbolic cosine. Or it's upside down. A hyperbolic sine or a hyperbolic cosine, but it's upside down. Okay? It's called a catenary curve. That's the only application, the main application. The other one would be the St. Louis Arch and the Gateway Arch in St. Louis. They use the hyperbolic cosine and hyperbolic sine, like, to make that. Okay? I'm not going to make you do a lot of work with those. I think just getting exposed to them, let's move on. But they work a lot like the trig group. They work very similar to the trig groups. There's also a hyperbolic tangent, which would be hyperbolic sine divided by hyperbolic cosine. Yeah, so. Now you said you did that one and you got an answer different than the book?
Yeah.
What was different about your answer?
The book's answer had a negative sign, mine had a positive.
So my guess is somewhere in there, one of those derivatives don't behave exactly the way you thought. Like, or one of the anti-derivatives. And I honestly don't remember which one. But I do know that, like, you know, the derivative of sine is cosine, the derivative of cosine is negative sine, but I don't think that's the case here. Think of, if I take the derivative of this, what am I going to get? E to the x plus e to the negative x. Right? If I took the derivative of hyperbolic cosine, I don't get negative sine. I get regular sine. That's why it was off. So, yeah, those are the hyperbolic cosines, hyperbolic sine. One year, we actually, this is kind of a funny story. They were decorating for prom at the Trinity. This kid named Kyle Brighton, I don't even know, this is a long time ago. He was on the group of people that had to decorate for prom. And they had to hang this like streamer thing from the ceiling. And he was trying to figure out like how much of it, he wanted it to come down so far. You know what I mean? So it wouldn't hit people's heads, but he wanted it to be down so far. And so like, it's like, oh, that's a hyperbolic cosine, hyperbolic sine. So we calculated using integrals the length of that, what is it called, streamer thing? So he would know how long he would need to make it and where he could tape it on the ceiling so it would hang down perfectly. Kind of a nerdy thing too, but you could have just trial and error it. And like, yeah, that's good enough, but other ones? Let's do a circle one. And then we'll also, if we have time, I'll teach you the rapido. What was that number 23? Of 2x?
Yeah.
Oh, that's lame. Okay. dx. What?
The x outside. The x to the right of the natural log of 2x.
Oh, yeah, and that was just me being stupid. So, right, I mean, you see, guys, right now, we don't have a choice. Right? You don't have a choice. It's what to make u and what to make dv. Okay? So, u is going to equal the sine of natural log of 2x. And dv is going to have to equal dx. Okay? What's du then? It's the cosine of the natural log of 2x, right? Times 1 over 2x times 2. And then dv, integrate that, you just get x. All right? So now when we go to the formula, we say it's u times v. So that's x sine of natural log of 2x minus the integral of v du. Now, Becca's our cancel girl. Can we cancel some stuff here when I do v du? that x and that x, the 2's cancel. So what are we left with? Just cosine of natural log of 2x. And then, of course, I forgot the dx. But. Okay? I'm curious, did anybody get to this point when they did this? You got to this point. Did you keep going? Or did you stop?
Well, I mean, I made you cosine.
So you kept going.
Yeah, but then I just stopped.
Okay? So you did the right thing by doing what you did. You just didn't know how to finish. Okay? If you've done enough of these integration by parts problems, at this point, you might even see it. Like, this is going to start to repeat itself. Okay? But maybe you don't see that. But as soon as you do what Ellie did, then you're definitely going to see it. All right? So Ellie said, well, I'm going to do what I know to do, and that's integrate by parts again. So I'm going to say u is cosine of natural log of 2x. dv is dx. And du is what? Negative sine of natural log of 2x times 1 over 2x times 2. And then what's v? Just x. And then you said u times v minus the integral of v du. And then where's Becca? Cancel all that crap. So x that, 2's that. So you're left with minus sine of natural log of 2x dx. Okay? And right here is where a flag should go. Now sometimes you get so involved with the problem, you forget what the problem was. But do you see that the problem that you have right now is the original problem? Does everybody see that? So what I'm going to do is this. I'm going to bring down this original problem right here, and I'm going to say, okay, well, I know the integral of sine of the natural log of 2x equals x sine of natural log of 2x. And remember, this minus is going to get distributed through here. Minus x cosine of the natural log of 2x. Minus, is minus. Okay, so do you see where we are? Now what are we going to do? You're going to treat this like an unknown and solve for it. So you're going to bring this to the other side and say, well, that means that 2 integral sine of natural log of 2x equals x sine of natural log of 2x minus x cosine of natural log of 2x. And then what are we going to do? Divide by 2. Or multiply by 1/2. So I don't want 2 of them, I just want 1 of them. Plus chips. Okay? So let me tell you where else that's going to happen, where the original problem pops up. It's going to happen if you integrate something like sine squared. It's also going to happen if you integrate something like e to the x times sine of x. Did you have any of those last night? I'm guessing you would have had e to the x sine. Cosine. E to the x cosine or e to the x sine. One of those two. It'll happen. Okay? So when the original problem pops up inside the integration by parts, just write it all out and set it equal to the original problem and then solve for it. It looks like a mess. I mean, doesn't that just look like mathematical vomit on the board? It really does. What time is it? 20, 21? 19, 20, 21. I don't think I have enough time to do the Rapido with you. So here's, I think, what I'm going to do. Keep working on these problems. If tomorrow, if you want, if you send me, like, tonight, if you want me to make a video of me working one of these out, contact me and say, can you work out problems, whatever. And then I'll kind of look at which ones I get, and then, so I don't have to do it 6 times. I'll work them all out at once. And then I'll put a video on for tomorrow. That sounds good.
Yeah. So you have to take the derivative parts twice in order to do it.
You mean when the original problem pops up? That almost, you'll integrate by parts twice for sure.
Okay.
Sometimes it might be 3 times.
Okay.
Actually, if my memory is right, it'll either be 2 times or 4 times. But I'm never going to probably have you doing one 4 times,
Okay.
because I think that's kind of absurd.
So you just keep doing it until you get the original.
Yeah.
Okay.
You're not going to have to do it more than twice.
Okay.
So. Oh yeah, let's see, where's my bag? They're black truffle oil and olive oil, not pepper. But there is a hint of pepper flavor. Not gonna lie.
They good? They tasty?
Huh?
Are they weird?
I don't think I count for a senior or something like that.
I don't think I responded to her. So forward it to her. I realize that after I sent it. Give me the verdict.
I think it's pretty good. It's a little weird.
Yeah, it's got a lot of flavor, but it doesn't feel like it's fake flavor. Like a Derek Burger. I'll take a picture of it.
Yeah, you better work close to your own success. Thing is, I was gonna wear a hat today. I know, I don't wear it. Yeah. It just made me look. It was just not the vibe. Because it was just this part of my hair like down. So it was like a thing. It was just not the vibe. Yeah, so I thought, this one is an easy one, so people will just it. I'll do like the college student spirit. Like, that's fun. I'll do that. I think it's on the other end across the locker. I don't know.
Or was it just read?
I just read, but I didn't actually do it. Well, I didn't get it long to finish the finals.
And even then, I was exhausted.
Yeah. Yeah. Like this 4:40. And then I do.
I left. 3:35, something like that. But I didn't get one over that. It was so hard. Because I just want to grab this. I literally stopped for 5 minutes to get that. That's right. And so I had someone that right stand. Yeah. I have to go again.
Yeah, I feel it too. We had these 3 people, they came in at 5:30. And I left at, no, we kicked them out at 10:15. They were still there. And they were like super drunk. And there was always like old people. And they would come up and like talk to my manager and was treating my manager was treating me. So he walked over and I'd be like, I don't know what to do. Like, I don't know how to do this. So I would just like stand there and like wait for
We
them.
forgot to forward or to reply to council along with myself.
Alright.
So,
I'm gonna struggle to stay awake for some class today. It's gonna be what? Sure.
Well, I want some.
I guess I'm not gonna say no.
I just figured it out. My advisory teacher gave us dinner.
Sure.
Yeah.
She. Good.
Sorry.
How can you know this one? Oh, yeah, I remember. You're her brother.
Because I won some like game the other day. You guys come over here. I'm not gonna make it.
Yeah, I think
Yeah.
I was working on the reindeer diet. So it's like this size. It was scary.
got one front one.
Regular inward diet. After.
I can do it. It's not very good, but I can do it. And then I can do a rock flip off the side of the thing. But when it's not very good and it really scares me, those ones behind it.
Jump backwards.
I do. What a long line.
Remember I eat that much strength.
Oh, man.
What's the matter? We're like 10 in.
I know, I saw you in the hall earlier.
I don't like to wear things.
I don't either.
I
So-
feel like I'm blocking people behind me.
This hat I've had for like 15 years. And when I bought this hat, it fit my head a lot better. I think my head has gotten fatter. I mean, first of all, it's a size S/M. I don't think when I thought it, I don't think I thought that stood for Scott Mitter. Like, I don't think I would buy a small to medium sized hat now if I were buying it. Just have to kind of do a yank down, and then it's kind of constricting, cutting off the blood flow. Do you work at G's?
No, that my uncle owns it.
Your uncle owns G's? No kidding. I used to go there a lot. Like, did they redo that place?
They moved the location.
Yeah.
No?
I used to go when it was at the other place.
Yeah.
Is it by Dorothy Lane Market now in Centerville?
Yeah, it didn't move that far, it was down a bit.
Just down the road, right? Yeah. Isn't it like where,
That's where we really.
what? Yes, right, yeah.
And the Alpaca Cross Line moved into a Sears Automotive.
Yeah. I like G's. They have good food.
I know. Wonder if they have more sushi.
We used to go there after football games. Back in the day, when it was at the other place. I feel like that was at the other place, and then they remodeled that on the outside. And then it was kind of looked new on the outside, but still the same on the inside. And then they moved to the other place. I'll be gone.
I didn't know it existed before where it is.
Really? Yeah, it was tucked way back there. You drive right by it, didn't even know it was there.
Where was it?
It was a secret. It was like a delicious secret.
Where was it?
I like Winans and Taco Bell.
Yeah, right behind Winans. Like it was there before Winans was even there. And then once Winans went in, like you really had to know it was there. Because there was no, you couldn't even see it from the road.
We're only a month away from getting potatoes back at Taco Bell.
We're only a month away from what?
Getting all the potato stuff back at Taco Bell.
Potato.
They got rid of like all their Fiesta potatoes and their cheesy potato grillers on my birthday.
I haven't.
Everyone I know has been super mad about it.
Yeah, I don't remember the last time.
Those were good. They have like red chips in them.
Well, I can tell you that until back in like probably early October, maybe September, I hadn't had Taco Bell in I don't even know how long. I mean, it might have been 20-some years. But Miss Britton loves Taco Bell. And back when we were online, she was here, like her kid was here. And somebody went and got her kid a bunch of, they had a bunch of burritos or something, I don't even know what they were. Something wrapped up in paper. And she didn't want them all. And her daughter's like, let's go give them to the swim guy. Because her daughter's like, she likes to swim, so I want to talk to her about swimming. And I gave her a swimming cap. And she wears her little swim lessons, so she thinks it's so cool. And so she brought me these two, again, I don't know what they,
Like the Doritos taco.
I don't know what it was. It wasn't, it didn't have Doritos in it. It was kind of thin. Just rolled up somewhere on a tortilla. It all tastes the
I go to
But
Beverly
really,
Hills.
these all places.
Oh,
same. But anyway, so let's talk some integration by parts, yeah? You feel good about this? You'd rather talk about tacos?
Yeah.
Taco Tuesday.
You never made us ribs for the exam.
Yeah, I never said I was going to. That was your idea.
It was our idea.
So, yeah. I haven't made any ribs in my smoker yet.
Really?
No, I've made smoked salmon, pulled pork, like wings.
My dad's favorite in the smoker.
you should bring.
Maybe I should,
You
you
should
know.
bring some.
Did you tell you that you know me?
He said so. He didn't know what he said.
It was so funny. I'll show it to you.
My friend's grandma had to make pulled pork for like healthier.
Oh.
So she substituted, just like she substituted the pork with tuna and the emergency sauce on it. It was disgusting.
You
I mean,
tried it?
Yeah.
What is that for dinner?
Tuna does not taste like pork.
You say you're going to make pulled pork healthier.
It was
Saying-
It was so
I
bad.
don't get all the places.
Well, people do that. I mean, pulled chicken is a similar
Yeah.
thing.
Yeah.
Yeah, that's really good.
I like pulled pork better.
I didn't.
All right, well, what questions do you all have? Because we got through, we did some things last period that we didn't do, or that we did here yesterday. Like we did that one problem that Mia asked about. We did that one in there. Which ones do you want me to work out that you don't know how to do? So many. Okay.
Did we work out number, I think it was number 23?
That's the one we did yesterday. The sign of natural
We
log
didn't
of x.
finish it.
Oh, we didn't finish it?
No.
Oh, you're right. We didn't finish it. Actually, it was natural log of 2x, I think. Okay, so I want to pick this up where we got to, because I don't want to necessarily go through all the same steps again that we did yesterday, because that would be sort of a waste of time. Like when we ended this, we had this, if I remember.
Yeah, we just finished the second.
Yeah. And I had written this down, and so we had x sine of natural log of 2x minus x cosine of natural log of 2x minus the integral of sine of natural log of 2x. I think that's where we were. I don't know about this, if that was a plus or minus. It was a minus?
Yeah.
So you might think that you're going to go in circles here. Okay? Because you see that original problem. Right? But when that happens, all you have to do is write down the original problem and then treat it like an equation. So solve that equation for the original problem. So if you see, I have them on both sides, right? So what I'll do is I'll add this one to the other side. So now I have 2 integral sine natural log of 2x like that. And I don't want one of or 2 of those, I want one of them. So what would be the next step? Divide by 2 or multiply by a half. So the final answer here is sine of the natural log of 2x equals 1/2 times x sine of natural log of 2x minus x cosine of the natural log of 2x plus chips.
Could you factor out the x in that as well?
Sure. I mean, it's not going to do anything for you, though. I mean, don't do unnecessary stuff just to, you're going to be so exhausted by the time you finish that problem. If you have the energy left to impress somebody with your factoring skills, I guess it's okay. So where does this happen? Like where you get the original problem popping up. Okay, 2 times I see this happening. Well, and the third time is this, because this is the first time I've ever done one like this. Like where the original problem popped up and it was not a product, literally a product of 2 functions. Okay? Where you see it more often, or where I've seen it more often, is when you have something like this. Like where you have an exponential in a trig, or you have something like this. Those are the 2 places where I see that original problem popping up. Where you have a sine squared or a cosine squared, where you have a exponential and a trig. Why don't we do sine squared? fun? You wanna do that? It'll be fun. I think it'll be fun. I'll try to make it fun. Mm-hmm. Oh, that's so offensive. Can you see that? Like see how it's all streaky? It's just so offensive. Okay, here we go. Ready? Sine squared x, baby. So how are we going to do this one? Well, we're going to say this is the same thing as sine of x times sine of x. Is that okay? So u is sine of x, and dv is sine of x. That's kind of whack. Okay, what's du? Cosine. And what's v? Negative cosine? Okay, you ready? So it's u times v minus the integral of v du. I forgot dx here. I always do. Are you happy with that? So now I've got negative now I've got negative sine of x cosine of x plus the integral of cosine squared of x. Yeah? So what do you think? What are we going to do? Do it again? Okay. So how about, I mean, what do you think? What are we going to let you and dv be? Just like we did before, right? Okay. All right. I mean, this seems normal, seems logical. What's du? Is negative sine of x, yeah? You really got to watch your SIGNs here. Okay, what's v? Sine of x, okay? Good. So u times v minus the integral of v du. Yep. Good? So what happens? We get add this to this. What do we get? This one's minus and that one's not minus. So I get 0. I love when that happens. 0 plus minus minus plus. So I have the inverse sine, or I'm sorry, the integral of sine squared plus 0. And that equals the integral of sine squared. Do we have a problem?
I mean, I guess it's technically true.
Yeah, we did all that work and we found nothing.
Yeah.
We just found that the antiderivative of sine squared equals the antiderivative of sine squared. And then just put undefined. That's what you do when you don't know the answer. No, what are you thinking?
After we, or before we did the antiderivative of cosine squared, we could have done, split it into cosine times cosine and then did a u sub. And
But the problem with that is if you do cosine times cosine, similar to this, but cosine times cosine, you can't do a u sub because in order to do that as a u sub, you need a sine and a cosine. Because the du is the other one. What if right here, rather than integrating by parts again, we got tricky with it? I believe that there's another name for cosine squared. Do you believe that there's another name for cosine squared? Cosine squared plus sine squared is 1, so cosine squared is 1 minus sine squared. So now I have that this equals negative sine of x, cosine of x, plus the integral of 1. Well, that'll be like this, x minus. You guys see where that x came from? If I antidifferentiate these each of individually, the antiderivative of 1 is x minus the antiderivative of sine squared. So there's the original problem again, right? But now it's not floating around with a bunch of nothing. So if I set it equal to the original problem, and I solve for it, I get that. But I don't want 2 of them, I want 1 of them. And then I'm going to rewrite this just so it looks prettier. How about that? What? That works? Jimmy, are you hot? I mean, I can put this hat on and I start getting hot. Samuel, your hat reminds me of this TV show on Netflix called Peaky Blinders. It's about this gang in Great Britain in the 20s, and they wear hats like that. And inside the hat, right here, they put these razor blades. So they take their hats off and they slice people with their hats. It's disturbing, isn't it?
Is it a flat cap or a new people hat?
Oh, I don't know. They just kind of look like those.
Well, because it's more rounded and more fitted to the head than new people Those are really popular in 1920s. That's why I asked.
Then maybe that was that. I don't know. I mean,
These were popular too, but this is a little different. This is a little bit flatter. They're all the same. They're all flat. They're all the same.
You don't have razor blades. Did you have a problem, like, I forgot this got snuck in there. Sometimes I give you problems where I know that you're not going to know how to do because I want you to have an experience with it. The problem 37 was not one of those necessarily. Now, the problem 37 was this. Did any of you do that problem? A lot of the folks in last period, they did that problem. They're like, I just ignored that H. I didn't know what that was. I just ignored it. So they just treated it like x times cosine of x. But interestingly enough, their answer was just off by a negative from what the back of the book said. So they're like, the back of the book is wrong. Well, maybe not in this case. So it occurred to me that those people, when they said they just ignored that H, they had never seen that function before, COSH of x, cosh of x. Neither of you, based on the way you're looking at me. Cosh are you talking about? Okay? Well, it turns out, my friends, that there are these functions out there called the hyperbolic trig functions. Okay? The hyperbolic trig functions. Now, I'm not going to make you memorize these or do anything, but it's nice that we're going to have a little exposure to them so that someday you could be sitting somewhere and maybe get an answer right on Jeopardy or. But the hyperbolic cosine and hyperbolic sine functions, you don't need to write this down. I may even have this backwards, actually. The hyperbolic sine function is e to the x plus e to the negative x divided by 2. And yes, that's just like the regular old e to the x function. The hyperbolic cosine function would be the derivative of this, which would be e to the x minus e to the negative x over 2. You see why the derivative is what it is? So these are called the hyperbolic trig functions because those functions, they behave like trig functions in their derivatives. Because the derivative of this, what would be the derivative of this? E to the x plus e to the negative x. So the derivative of this is this. It's not negative though. Okay, there's also a hyperbolic tangent, which is this divided by this. Right? Now, who cares? Who came up with this? What is that? What do these functions even mean? Okay, they're called hyperbolic trig functions, so we already got the trig connection. Their derivatives sort of behave like trigs, right? They're called hyperbolic because their graphs can sort of have a resemblance of a hyperbola. You guys know what a hyperbola is? Okay. The most significant, in my mind, application of these functions you see every day when you're driving down the road, and you don't even know. If you take a cable or a rope or an electrical wire or a telephone wire and you fix it, if you hold it at this end and you hold it at this end, and then you just let it dangle with gravity. Like that shape that it makes is not a parabola. It looks like a parabola. But that shape that it makes is actually a perfect hyperbolic cosine sine curve. Okay? Also, anybody ever been to the Arch in St. Louis? The Arch in St. Louis, which is, it looks like a parabola. But it's not. The Arch in St. Louis is actually, I kid you not, it was constructed by a bunch of it has triangular cross sections. So like if you were to slice it, it would just be a triangular shape. And I don't know is that the orthocenter? The middle of those triangles, let's just say the middle, that's kind of a nice random generic word. The middle of those triangles, if you connect them all, is a hyperbolic cosine curve. You can actually go online and look it up. The equation of the curve that they use to make these equals. Okay?
What's the difference between that and parabola? Like, if it looks like a parabola, obviously it isn't because you just said it was, but like.
Well, it's not because, the points on the curve aren't the square away from the previous one. You know what I mean? Like, that's why it's not. I mean, they just have similar shape. Now, when it comes to like the like construction thing, I mean, they just decided to use that. Maybe they used that because of some sort of strength thing of the stones and the concrete and all the stuff that they were using to build the arch. I will say that if you think about a bridge, a suspension bridge, you ever seen a suspension bridge? So a suspension bridge typically has a big cable like this. And then here's a tower and here's a tower, right? And, this is a cable that's just dangling. But the difference between that and a suspension bridge, if there was a suspension bridge involved, the cable's just not dangling. What else is there? Do you know? Yeah, these pieces, what are these right here? These are cables that are hanging from the cable. And these cables are holding up the roadway. When a string or a cable fixed at two ends then has cables hanging off of it, that is a parabola. But when you take away the cables hanging down, it's not a parabola. That makes sense? So like when these things are hanging vertically and they're carrying a uniform load like this bridge or this road deck, this curve of the main cable would be in the shape of a parabola. But if the cable's just hanging there, it's called a catenary curve. Yeah.
So what do you use the equation? Like, that's what do they use it for practically?
Well, you could,
For construction and stuff?
maybe. I'll tell you a quick story where we used it one time. It was back in like 2005. We were in calculus class. They were decorating for prom. And this kid named Kyle Brightman, I don't know how I knew this. This kid named Kyle Brightman, he's like, Mr. Spinner, I want to hang this streamer from the ceiling. Like this thing hanging down, like these streamers, where we hanging down. He's like, but I want it to come down so far. I don't want it to like get in the way, but I want it to come down, so it's so low. Like, well, that's a catenary. Like if you tape it up here, it's just hanging by its own, gravity, right? So we use calculus to find the length of the streamer by integrating those functions. And he found the length of what that streamer had to be so that it would come down, so that Carrie wouldn't hit it when she walked underneath. Does that make sense?
Yeah.
Now, it was way overkill. We could have just had a ladder and had some tape and like, okay, is that low enough? No, maybe a little lower. Okay. Well, this, yeah, my way was a lot more fun. I mean, and less dangerous.
Well, one part put up there, so, you know, it's not a lot of fun.
Okay, well, what other ones do you want me to work out? So I guess the moral of the story is you don't necessarily have to worry about 30s that time. Other ones that you want to work out? Jamie, is that a hand or are you just playing with your little, huh?
It's not a hand.
It's not a hand? I didn't know if you were just playing with a little
Yeah.
fuzzy thing on your hat. Yeah. 29? What is it?
It's the integral of the inverse cosine.
Oh! Didn't we do an inverse yesterday in here? Okay. Yeah. Like that? Okay. So we did this one last period. I knew we did it. So we're going to have to say u is inverse cosine. dv is dx. This is problem number 29, you said? Cool. All right, so what's du? Well, it's negative 1 over the square root of 1 minus 2x squared times 2. And what's v? Just x. All right, so u times v minus the integral of v du. Oh, I forgot dx up here. So that'll be negative 2x over the square root of 1 minus, I'm just going to go ahead and call that 4x squared, if you don't mind. So minus minus, what happens there? Turns into plus. So what are we going to do here?
Factor out of 2x.
You could. I mean, you could do that. But if you look very carefully here, this doesn't have to be done by parts. This can be done with a u sub. Because you've got 4x squared inside that radical, right? When you take the derivative of that, you get 8x. There's the x that you need for the du. So we're going to do that with a u sub. So I'm going to do my bracket thing, even though I'm not integrating by parts. U is going to be 1 minus 4x squared. What's du going to be? Negative 8x. So du over negative 8 equals x dx. Billy, do you want to move? I mean, if you want to sit over there, I feel like you have a tough seat to sit in. To see. Talk to me.
Is you do du over negative 4 2x dx?
Yeah. That's going to happen here in a second. So when I do this, I'm going to get negative 1/8, right? Times the integral of 2 du over radical u. And then that's going to end up being what Samuel just said, negative 1/4 integral u to the negative 1/2 du. So what's the antiderivative of u to the negative 1/2?
1/2 for u.
Not 1/2. You add 1 to the exponent and you forgot to flip it. So it's 2u to the 1/2. You see what I'm talking about? Yeah. So it's going to be negative 1/4 times 2u to the 1/2, or negative 1/2 times radical u. So now, this isn't the final answer. The final answer is going to be x inverse cosine of x, 2x, x inverse cosine of 2x, plus negative 1/2 square root of u. And what was u? 1 minus 4x squared, plus chips. Yeah.
Is there a big difference in use between using the minus 1 power inverse and using
No.
that sometimes there can be.
Yeah, in fact, if you, like in the AP environment, they don't use the negative 1 power. They always use arc. And they do that just so kids don't accidentally make the mistake of treating it like that as 1 over cosine of 2x. Yeah. And actually, if you do programming and you want the inverse cosine of 2x or the inverse sine of 2x, you would have to use arc because the computer would get confused. Because to the negative 1 power, right? It's going to think that's the reciprocal. So it uses the term arc.
It is kind of an odd motif for they use the negative 1 power for the inverse.
Well, it's because the negative 1 power, like, it's the reason why it's because we use this right here to represent an inverse of a function. And the negative 1 power is an inverse. It's the multiplicative inverse. Because if you think of the negative 1 power is the inverse operation of multiplying. What's an inverse operation? What does that mean? Well, you're thinking about the function. An inverse operation is when you do this, and you do this, and you get the identity. So when you inverse multiply, what do you get? 1. When you inverse functions, the identity function is x. Like when you stick inverse sine into sine of x, like sine of inverse sine of x, that's x. Like they undo each other. We actually have a very just from our, like, you know, our heritage, our mathematical heritage, our understanding and working of inverse relationships is very, very limited. That's why we struggle sometimes with that notation. We get it all. So here's the dealio. You need to keep working on these problems. If there's some that you want me to work out, email me, and I will make a video of me working them out tomorrow. Or I can even set up a time like where I can just go online and do a live Zoom or something, work out problems like office hour kind of thing. But we're getting close to the end of integration by parts. We got to move on to the next thing here soon. So we'll probably have, I didn't tell the last class this, we'll probably have a quiz on this on Thursday or Friday. Probably Friday, actually, not Thursday, because I don't see you tomorrow. If I were going to see you tomorrow, we would have a quiz. But this Wednesday off, then it's yeah,
Are we gonna learn those like shortcuts that you talked about?
yeah, I'll probably teach you that on Thursday. Well, have a good afternoon, my friend. Yeah, I'll just show this email.
I'll see you in a bit, Mr. Bitter.
See ya.
So, you only have to take a computer program.